Okay, so we're going to finish the course with two presentations about particle physics, and this first presentation in this video is going to look at the history of how the different particles were discovered and the development of the theory behind those particles. Okay, so this first slide is just a kind of brief summary of how the theory of particle physics developed. So the very first subatomic particle discovered was the electron. It was actually predicted slightly before it was discovered that there should be some sort of subatomic particle carrying the electric charge responsible for electricity, and this was discovered in 1897. We'll talk about the discovery in a bit more detail in the next slide. Okay. Then after the electron, you know that the atom must be made up of some other things other than the electron, and the proton was discovered by Rutherford in 1919. Before that, as we have already seen with the blackbody radiation and the photoelectric effect, the photon was also hypothesized to exist and then discovered on the basis of those experimental evidences in 1905. 1905 is the date of Einstein's explanation of the photoelectric effect. Okay. Then later on, another particle called a neutrino was predicted to exist. I'll explain why later. And the first prediction of antimatter was in 1931, and this was the antimatter particle for the electron. Then after that, the neutron, surprisingly, the neutron, because it makes up most of the matter around us, it was discovered relatively late in 1932, and I'll explain the reason for that. The positron was discovered just 1 year after it was predicted, also in 1932. Then the muon, which we talked about in the special relativity section, when it was one of the tests of time dilation effect, that was discovered in 1936. The antiparticle for the proton, the antiproton, was discovered in 1955. And finally, on this slide, the neutrino, which was predicted in 1930, was eventually discovered in 1956. Okay, so the next few slides go through some of these discoveries and talk about how they were made. Okay, so this first one is the discovery of the electron. And well, exactly what discovery means you can argue about, but most people credit this guy, J.J. Thomson, with the discovery of the electron. And what he found was that if you have what's known as a cathode ray tube, which is where you have a very strong electric field which can actually pull some of the electrons off of atoms of gas which are inside the tube here, then the electrons are accelerated through the electric field gradient in this direction. And if the electrons hit some of the other atoms in the gas, then they cause this glow. Okay, so you can see these cathode rays, as they're known, by a colored glow in the gas, which the glow actually comes from the energy levels of the electrons inside atoms, which we've talked about in the previous lecture. Okay. So what J.J. Thomson did is he took these cathode rays and he applied a perpendicular electric field to the system like this, and that, because the electrons are charged, causes them to deflect, and their acceleration, which you can measure in this experiment. It is not working. Okay, just a second. Yeah, okay. Their acceleration of the electrons, which you can measure in this experiment, is equal to force divided by mass, right? And the force on the electron is proportional to its charge, like this way. So because you know the electric field, doing this experiment allows you to measure the ratio of charge to mass of the electron. And it was found that this ratio was very large, much larger than, say, the charge-mass ratio for a hydrogen atom, which was ionized. So this kind of gave evidence that the electron was some kind of very light particle, much smaller than atoms. But it wasn't a direct measurement of a single electron mass or charge. That came later in something known as the oil drop experiment, which was in about 1919. But anyway, the discovery of the electron is usually credited to J.J. Thomson in 1876. Okay, so this next slide talks about the discovery of the proton. So this was discovered by Rutherford, who first of all discovered the atomic nucleus. So that experiment is the topic of one of the student presentations, so I won't talk too much about it. But anyway, that experiment also used alpha particles. Alpha particles are basically a helium nucleus, 2 protons and 2 neutrons, and they are naturally emitted by very large radioactive atoms. And Rutherford was using this radioactive emission to study the behavior of atoms. Okay, and in 1919, one thing he found is that if he fired these very high energy alpha particles into a nitrogen gas, then he could get some of the nitrogen nuclei to turn into oxygen nuclei. Okay, and in the process of doing this, 3 of the particles, 2 neutrons and a proton from the alpha particle, are absorbed into the nucleus, which turns it into oxygen 17, and the remaining proton escapes and is free. Okay, and he was able to detect these free protons and again measure their mass and charge. Okay, incidentally, by doing so, he automatically showed that the neutron should also exist, right? Because we knew the mass of these atoms, and now the electron and the protons had been discovered, but there wasn't enough mass just from the electrons and the protons to explain the whole mass of the atom. So it was known there must be something else in there, which was the neutron, but that was discovered much later. Okay, so now we come to the neutrino. So this was one of the particles that was predicted a long time before it was discovered. And it was predicted on the basis of indirect evidence. So another kind of radioactive decay, different from alpha decay, is beta decay. And beta decay is where an electron is emitted from the nucleus of an atom. And it was thought at the time that what was happening is that inside the atom you have many neutrons, and one of these neutrons can turn into a proton and an electron. Okay. So that was the understanding of beta decay in the 1930s. But when they started to do some experiments measuring the conservation of energy and momentum in this reaction here, they found that energy was not conserved, and neither was momentum. Okay, so most of the kinetic energy is carried by the electron, because the electron is much lighter, so it's emitted with a much higher speed. But if you were to measure the energy of the electron which is emitted, then conservation of energy would predict for you a certain value of emitted energy here, the kinetic energy of the electron, which is based upon the difference in mass, the change in mass of the nucleus when the neutron turns into a proton. That tells you how much extra energy must be created, right? And that predicts a value somewhere here on this plot. But then if you find the actual energy of the electrons emitted in experiments, then they have some amount of energy less than this. Okay? So the predicted value of energy that every electron should have experimentally was just the upper bound. You didn't find any electrons with more energy than this, but you found lots of electrons with less energy than this. Okay, and Pauli suggested an explanation for this. Basically, he said, suppose you have an electron which has energy here, then the gap in energy here, which must go somewhere if energy is conserved, is carried away by some kind of new particle which we can't detect for some reason. Okay, and this new particle was eventually named the neutrino. Okay. So one thing you can see from the neutrino, so that means that now the neutron actually decays into 3 particles, a proton plus an electron plus a neutrino. Okay, and in particular this there are different kinds of neutrino. This one actually is an anti-electron neutrino for reasons that will be explained in the next video. You see from this equation that the neutrino must have zero charge, right? If we look at the charge of all the particles here, then the neutron has zero charge, right? The proton has charge of +1 electron charge. The electron has charge of -1, and therefore, to conserve charge, the neutrino must also have zero charge. Okay. And the main reason that the neutron and the neutrino were discovered later, much later than the other particles, is because of this fact. It's very much easier to detect a particle like a proton or an electron using the electromagnetic force, right? If they have charge, then they interact with electric and magnetic fields, and this means they also will interact with other atoms and things as they go past, because the atom is bound together by electromagnetic forces, right? And this makes them much easier to detect. So generally in the history of particle physics, those charged particles were detected much earlier than the non-charged particle. Okay, because if they don't have charge, the only way you can detect them is by some other kind of interaction. Okay, so the neutron was detected because it interacts with other nuclei, okay, through something known as the strong nuclear force, and that was how it was able to be detected. And the neutrino actually does not interact by this strong nuclear force, so it's even harder to detect than the neutron, and it was eventually detected through a different kind of interaction known as the weak nuclear force, which we will talk about in the next video as well. Okay, so then now we move on to the discovery of three particles, the positron, the muon, and the antiproton. So I put these together because they were all discovered at about the same time in the 1950s, 1930s, and also they were discovered in the same method. So the method is, you have what's known as a cloud chamber here, and a cloud chamber is a chamber, so a kind of big vessel. So these things are really big, sort of several meters across, and in here you have some sort of vapor. Usually it's some alcoholic vapor, okay? And this vapor is what's known as supersaturated. What supersaturated means is ordinarily it would like to turn into a liquid, okay? But the fact that you prepare it very carefully, in order for a gas to condense, to turn into a liquid, it needs to have some kind of trigger, okay? Which can be some kind of dust or dirt mixed in with the gas, around which the gas particles can condense into liquid drops, or it can be some sort of shock wave going through the system. But if you prepare the system very carefully as a gas and then reduce the temperature, then if you do this very slowly and without any sort of noise in the system, it will actually remain as a gas to much lower temperatures. And this is what supersaturated means. And this means whenever there is some sort of noise or shock going through the system, you get these gas particles condensing into liquid. Okay, and in particular, if a charged particle comes through here, like this is the path of a charged particle, then along the path of the charged particle you get places where all of the gas particles have condensed, and then what you see, hopefully you can see in this picture, this is actually the original picture from the discovery of the positron. You can see this line here. So this line is actually a line of very, very tiny drops of liquid where the charged particle has gone through and disturbed the supersaturated gas in the cloud chamber. So it's called a cloud chamber because a cloud, right, is a collection of very small liquid water droplets. And in the same way here, this line is a collection of very small droplets of alcohol liquid inside the cloud chamber. Okay, so inside these cloud chambers they put a magnetic field across, And the reason they do that is because then charged particles will curve because of the magnetic field, and again the curvature of this path here, this path here, the curvature is again proportional to the charge mass ratio of the particle. Okay, so when they discovered the positron, what they found is they found a path through the cloud chamber like this. They saw that the charge mass ratio was exactly the same as the electron, but with the opposite charge sign, and this is how they were able to identify it as being a positron. Right. So one more thing I will say about this slide before we move on to the next one. This positron and antiproton are the first examples of something known as antimatter. So this was first predicted by Dirac in 1931, okay, so just before these particles were detected. And it's interesting where this prediction came from. So the quantum theory of Schrödinger that we talked about in the previous videos is not a relativistic theory. So in other words, it only works if you take the momentum of particles as being like mass times velocity and so on, and a Galilean transformation between different coordinates, right? But now we know from the theory of relativity that this is not okay, right? In reality, the formula for momentum is different from this when you approach the speed of light, and also the correct transformation between reference frames is the Lorentz transformation, not the Galilean transformation. So Dirac was trying to make a theory of quantum mechanics which is consistent with special relativity. Okay, and he was able to get somewhere along this lines. To get the full theory took a long time, actually, but he was able to make some progress in combining quantum mechanics and special relativity, and one of the consequences of this was the prediction of antimatter. So this means whenever you have a kind of particle which has some kind of mass, and some charge, there must always be another kind of particle which has the same mass but has exactly the opposite charge, okay, which is called the antiparticle. For each time you have an electron, you must have another particle which has the same mass but the opposite charge of the electron, and this was known as the positron. Okay, so after those discoveries, which were all sort of in the 1930s, 1940s, after the Second World War, particle accelerators started to be made. The previous discoveries were all particles which were created either in cathode ray tubes or detected coming out of the atmosphere. For example, like muons we talked about are created in the atmosphere, and they were detected like that. But the idea of particle accelerators is that we can actually create some of these new particles by colliding existing matter together, atoms or protons or things. Most accelerators now use protons. You accelerate them and you collide them together at very high energies, and if you're lucky, then some of the energy in the collision can go into creating a new particle. Okay, and this particle again you can detect using something like a cloud chamber or other detecting device. Okay, so the most modern example of a particle accelerator is the Large Hadron Collider, which is in Switzerland. So this you can't actually see because it's built underground, but this is a photo taken from the air, and this line here is drawn onto the photo, but this is where the particle accelerator lies under the ground. Okay, and the total distance around here is absolutely huge. It's about 26 kilometers. Okay, and the reason it's so huge is to get enough energy to create these kind of high energy particles you want, you have to accelerate the protons which are going around here to incredibly high velocities, very, very close to the speed of light. And as we saw, if you approach the speed of light, the momentum diverges, So these protons have a huge amount of momentum, so it takes a lot of force to get them to curve, and therefore the curvature of their path, in order to make it not so large so that you can apply enough force to keep them curved, you have to make the radius of this circle very large indeed. Okay, a smaller circle would mean more curvature, which means you have to apply a stronger force to keep the protons moving in a circle. Right, so these particle accelerators started to be built in the 1950s, and then that led to the discovery of a huge number of new particles, because we were now able to control things like the energy and the nature of these collisions, and lots of different particles were discovered. Okay, so this is some pictures inside the Large Hadron Collider. So this is actually the beamline, which is where the protons are carried. So inside here you also have lots of electromagnets which are applying the force to keep the protons moving in a circle. If you look at this picture, you can see it is slightly curved, right? So this is the arc of the circle going around here. And every now and again, I think in about 5 or 6 different places in this circular loop, you have these detectors. And this is where the two beams of protons, which are traveling in opposite directions, are brought together and collided. And then any particles that are created in those collisions are detected by these sort of detectors. Okay, so you can see they're absolutely enormous, right? This is people standing in the foreground. So this is about 4 or 5 stories high, this detector here. Right, so as I said, because of those particle accelerators, huge numbers of new particles were discovered. So actually like hundreds of different kinds of particles. And this caused quite a lot of confusion, because before that, all of the particles were discovered were kind of necessary from the theoretical perspective. So, first of all, the electron was discovered. That was necessary to explain the nature of electricity. Okay, and then after you discovered the electron, you knew there must be something else in the atoms, and then the proton was discovered. And then the mass of the atom was more than just the mass of protons and electrons, so you knew that the neutron must exist. We knew the neutrino must exist because of beta decay. Energy was not conserved. We knew the antimatter particles must exist because of this prediction of Dirac. So the particles that are discovered before, there was kind of a reason for each of them. But these hundreds of particles that were discovered in the 1950s and 60s, there was kind of no explanation of why they should exist. Right? They don't seem to be present at all in the everyday world that we see around us. And at first, there didn't seem to be any pattern in their nature in terms of their masses or their interactions and so on. Okay, but lots of physicists were working not only to discover these particles, but also try to explain their properties, and eventually a simple explanation to all of these particles was made. Okay. So first of all, you can divide the particles into fermions and bosons. As we saw in the last video, all quantum particles either have this fermion nature or boson nature, which is a property of how a system of many particles interact based upon their indistinguishability. Okay, so fermions were named as baryons that were discovered in these particle accelerators, and the bosons were named as mesons. Okay. So within the baryons, there were a few particles that we already know about. For example, the proton is here, the neutron is here, but the others are all new particles. And the mesons were entirely new. None of the mesons had been discovered before. Okay. Right, so this mess was simplified a bit by the invention of the quark model, which was in 1964 by Murray-Gell-Mann and also Zweig. So their idea was that just like if I have an atom is made up of a number of neutrons and protons surrounded by a number of electrons. the idea of the quark model is all of those hundreds of particles, the baryons and mesons, explained in the last slide, could also be built up of smaller particles. And these smaller particles were these quarks. Okay. So we now think that there are total 6 different kinds of quark, which are shown down here. The original theory of Murray-Gell-Mann only had 3 kinds of quark. Oh, sorry, not that one. These 3. The up, down, and the strange. Because that was enough to explain all of the particles that were discovered at that time. But later on it was found that more were needed to complete the theory. And eventually, up until now, there are 6, and we think 6 is enough to have a consistent theory. Okay. So if you look at these squares here, this is the first time that they have been represented by this. So this is showing some information about each of the particles. So the top number here is the mass, measured in electron volts over c squared. Then you have the charge, that's measured in units of the electron charge. So the electron has charge -1, proton has charge +1. Then the third number down here is the spin. So if you remember from last lecture, there's the spin statistics theory, which says that any fermion must have half integer spin, and any boson must have integer spin. So these quarks all have half integer spin, spin a half, right? And therefore they are all fermions. Okay. And the idea was, by putting these different quarks together in different combinations, you could make fermions, you can make the baryons or mesons. In particular, a baryon is made up of 3 quarks put together. So for example, the proton is combined of 2 up quarks and a down quark. A neutron is made up of 2 down quarks and an up quark. Okay, and you can see if you add together the charges, you get the right answer. So 2 ups is 2/3 plus 2/3, that's 4/3, and then down is -1/3. So that gives you charge of 1, which is right. And for the neutron, 2 downs is -2/3, plus 2/3 for the up quark gives you 0. Okay, so this predicts the right charge for all of these different particles. Okay, and the bosonic particles, the mesons, were composed of 1 quark particle and 1 antiquark. Okay. So antimatter applies to everything, so it also applies to quarks. So for each quark, you also have an antiquark. So for example, here, one of the mesons, the lightest meson is the pion, and that's made up of 1 up quark and 1 anti-down quark. Okay. This bar, by the way, is a standard notation. If you put a bar on top, it shows that you're talking about the antiparticle. So if the electron is written as E, then the positron is written as E bar. If the proton is written as P, then the antiproton is written as P bar, and so on. Okay. So this theory was very successful. It was shown that all of these new particles that were detected, the baryons and mesons, could be explained within this quark model. Okay. Right, so this is the final slide on this presentation. So this slide is introducing what's known as the standard model, which is a list of all of the fundamental particles we have, good evidence for in the universe at the moment. So in this slide, you can see here are the 6 quarks, which were talked about previously. There's also these things called leptons. So these are things which are not present in the atomic nucleus. So the electron is the most obvious example. That's a different kind of particle, not made out of quarks. And we saw that there must be this neutrino predicted by beta decay. The muon is also similar to an electron. In fact, the only difference, the most significant difference between the electron and the muon is its mass. It has the same charge, it has the same spin, but the muon is about 200 times heavier. And later on it was predicted and then discovered that there was a third particle which was like the electron, but heavier again. So this one is about, is it like 1,000? This is about 3,000 times heavier than the electron, and this is known as the tauon. which was discovered in the 1970s, 1973. And each of these has its own neutrino. So the muon has a mu neutrino, the tauon has a tau neutrino. These all have very, very small masses. In fact, we've never been able to measure the mass of a neutrino. There are lots of experiments going on at the moment to try to measure the neutrino masses, because we know they're not zero, but we haven't been able to measure any answer which is greater than zero either. So that's a bit of a puzzle at the moment. Okay, so these quarks and leptons are all of the fermions in the Standard Model, these 12 particles here. And you also have the bosons, which are these particles in red, which are called the gauge bosons, and the Higgs boson as well. Okay, so in the next presentation, I'm going to talk about what these bosonic particles are. Okay, so that's the end of this presentation.